All right, today we're going to take a journey, a deep dive right into the mathematical engine room of modern physics. We're heading straight for the heart of string theory to explore this remarkably powerful, beautiful idea called conformal field theory. It's basically the language that physicists think describes the universe at its most fundamental level. So here's our game plan. First, we're going to look at the perfect, almost magical symmetry of a single string. Then, we'll zoom way in to see what happens when quantum fields get really, really close to each other. From there, we'll uncover the fundamental laws this symmetry actually enforces, which is going to lead us to the master blueprint of the entire theory, something called the Virasoro algebra. And finally, we'll zoom back out and see why this whole structure is one of the most powerful tools in all of theoretical physics. It's going to be great. Okay, first things first. When physicists talk about string theory, you might picture this tiny one-dimensional line wiggling around. But that's not where the real action is. They're actually focused on the two-dimensional surface that the string traces as it moves through space-time. This surface is called the world sheet, and it's everything. All the physics we care about happens right there. So that immediately brings up a huge question, right? If all the important stuff is happening on this 2D surface, what's the right mathematical language to even describe it? I mean, what are its most fundamental properties? Well, it turns out the answer lies in this very special, very particular kind of symmetry called conformal invariance. Just look at this grid on the screen. See how it can be stretched or shrunk or warped, but the angles stay the same. Every single corner is still a perfect 90 degrees. That property, preserving the angles no matter what, is the absolute key to everything we're about to talk about. And that brings us right to the main event. A conformal field theory, or CFT, is basically any quantum theory that has to obey this angle-preserving symmetry. Now, in our normal four-dimensional world, that's kind of neat, but here's the kicker. In the two dimensions of a string's world sheet, this symmetry goes into overdrive. It becomes incredibly powerful, so restrictive that it practically locks the theory into a super rigid structure. And for a physicist, that rigidity is a dream come true because it means the theory is incredibly predictive. Okay, so we've got this super powerful symmetry. Now, how do we actually use it? We need to build a toolkit for working with these theories. And to do that, we've got to zoom right in on our world sheet and ask a very basic question. What happens when the quantum fields that live there get a little crowded? This is truly one of the most fundamental questions in all of quantum field theory. You've got these things called operators. You can just think of them as little markers for fields or particles at a specific point. So what happens when you bring two of them so close together that they're practically on top of each other? How in the world do you describe that interaction? So imagine these two operators on our 2D surface, one at point Z1 and the other at Z2. As they get closer and closer, their interaction becomes this incredibly complicated quantum mess. But what if you step back? If you zoom out and look at that combined blur from far away, what does it actually look like? The solution is this amazing tool called the Operator Product Expansion, or OP. It's essentially a rule book. It tells you that you can replace that whole complicated mess of two nearby operators with a single equivalent operator, plus a bunch of simpler corrections. It's kind of like the quantum version of saying, from across the room, those two people whispering just look like one person talking. It simplifies things beautifully. All right, so now we have our rule book, the OPE, but we can't just use it however we want. We have to look at the laws that our conformal symmetry imposes on it. Because in physics, you have to remember a symmetry isn't just some neat, pretty feature. It has real, hard and fast consequences. Seriously, this is one of the deepest truths in all of physics, all the way from basic mechanics to cutting-edge string theory. Every single symmetry implies some kind of conservation law, a rule that the universe absolutely must obey. In our conformal symmetry, it's no different. These consequences are expressed mathematically through something called ward identities. You can think of these as the enforcers, or the police, of our symmetry. They're equations that go through and check every single calculation to make sure that the rules of conformal symmetry are never, ever broken. Every interaction we describe with our OPE rulebook has to obey these identities, no exceptions. And now, this is where it all comes together. We've got this incredibly powerful symmetry, and we've got the OP as our rulebook for how things interact. When you combine them, when you force the OP to obey the strict laws of symmetry, something absolutely stunning emerges. A rigid, universal blueprint for the entire theory. So to really unlock this deep structure, physicists use a really clever mathematical trick. They take the world sheet of a closed string, which as it moves through time looks like a cylinder, and they mathematically map it onto a flat plane. It's a change of coordinates, a change of perspective that makes the hidden symmetries way easier to see and work with. Now, every single CFT has a master operator called the energy momentum tensor. We'll just call it T. It basically contains all the information about energy and momentum in the system. And here's the wild part. When you take our OPE rulebook and apply it to this master operator interacting with itself, you get this big, complicated expression you see here. Now, don't worry about reading the math. The only thing you need to know is that hidden inside all those terms is the secret grammar of the entire theory. Because by taking that OP and applying the rules, the ward identities, you can actually decode a hidden message. You can extract the fundamental relationships that govern all the generators of the conformal symmetry. It's like cracking a code. And this right here is the decoded message. This equation is the versatile algebra. It is the fundamental blueprint that governs any possible two-dimensional conformal field theory. It's incredible. All the properties of the theory are encoded right here. And for us, the most important piece of this whole thing is that one little number c on the right-hand side. It's called essential charge, and its value is like a unique fingerprint that identifies exactly what kind of theory you're dealing with. Okay, let's zoom out for a second. We've just uncovered this pretty abstract-looking algebraic structure. So what? What does it actually let us do? Why is finding something like the Virasoro algebra so important? Well, the power of this thing is just immense. Because it's a universal structure and because it has this infinite complexity, it constrains the theory so tightly that it actually becomes solvable. It lets physicists calculate things exactly without having to make approximations, which is a rare, rare luxury in quantum physics. Just by knowing the value of that one number, c, the central charge, entire families of physical theories can be sorted, classified, and completely understood. This algebraic backbone is what takes string theory from just a collection of cool ideas and turns it into a real, calculable, predictive framework. And this quote really just nails it. You see, in most other theories, symmetry is just one nice feature among many. But in a 2D CFT, symmetry is everything. It's the whole story. Once you define the symmetry, the entire theory, all its particles, all of its interactions, is pretty much completely determined. And that's what transforms a system that could be totally chaotic into something elegant, solvable, and, well, beautiful. And all of this leaves you with a final, really fascinating thought. As we keep searching for the ultimate laws of nature, we keep finding that our most powerful, most profound ideas are all based on principles of symmetry. So it makes you wonder, doesn't it? Could it be that at the very bottom of it all, the fundamental logic that governs reality isn't a particle or a force, but just a perfect, unbreakable symmetry?